Hello everyone. Today my topic is quenching. Quenching is a process defined as one which competes with spontaneous emission process and thereby shortens the lifetimes of the emitting molecules. Quenching reactions are basically energy transfer processes from an excited state of a molecule to ground state acceptor molecule. Quenching of excited state mercury atom by ground state rare gas atom can be represented through this figure, which is known as total physical quenching. Ground state rare gas atom is the quencher. In my earlier video, I have made about sensitization and how the transfer of excited electrons takes place. Do watch that video to get a better connectivity. Now in this graph, it is a graph of potential energy versus interatomic distance r. Curve 1 represents the potential energy of the system Hg, mercury plus argon, as the function of interatomic distance r. Curve 2 is the potential energy curve of ground state atoms of mercury and argon. At a very small value of interatomic distance Rx. Here, these two curves will intersect. So this is the intersection point. If a collision between excited mercury atom and a ground state argon atom is sufficiently energetic that they approach with a distance of Rx, a rearrangement of electronic energy levels of the excited mercury atom to those of the ground state would permit the system to cross over curve 2, resulting in the ground state atoms of mercury and argon. However, the excitation energy will be distributed among both mercury and argon in the form of kinetic energy. This is an example of total physical quenching, where entire energy of the excited state has been converted into kinetic energy. In the presence of a quencher molecule, the given excited state molecule will undergo this type of process. I'll show with S0 plus H nu is the irradiation that has been absorbed. In presence of K0, it enters S1. That is excitation state. Here the rate will be IA. This singlet state S1, it again goes into IC to give S0 plus heat. IC stands for internal conversion. Therefore, the rate will be KIC concentration of S1. This further will undergo intersystemic crossing. KISC to enter T1 state, triplet state, along with heat. Systemic crossing, which is written as So therefore the rate will be KISC at S1 state. This S1 singlet S1 state, it emits fluorescence to go back to the ground state with HVF. So the rate will be KF S1 state. Now we take up triplet state. The T1 state undergoes phosphorescence. So it is Kp to go back to the ground state, that is HVP, phosphorescence. So Kp, the rate will be Kp, since it is a triplet state, at T1. The T1 state now undergoes triplet, or you can say reverse intersystemic crossing to go back to ground state along with heat. Reverse intersystemic crossing. In terms of rate, it will be written as K TISC state. S0 stands for ground state. S1 and T1 are the singlet and triplet excited states of donor molecule, and this all is the expression for rate. Applying this steady state approximation for S1 state, rate formation of S1 will be equal to rate removal of S1. Formation will be equal to removal. That is, rate of formation S1 is equal to I. So S1 is removed in internal conversion, intersystemic crossing and fluorescence. IC, ISC and fluorescence. So the rate of removal of S1 will be equal to K internal conversion S1 plus K ISC S1 intersystemic crossing S1 plus K fluorescence S1. Therefore, we can say K IC plus K ISC plus K F S1 is equal to IA. Therefore, S1 can now be written as IA divided by KIC plus KISC plus KF. So in general, for any excited state molecule of D, which is represented as D star, will be D star is equal to IA divided by this whole term as C. Or we can also write it as, in terms of concentration of excited state molecules in absence of quencher molecule, it can be written as IA divided by Kf plus summation of K1. If another molecule Q is added to the solution, which quenches the fluorescence by a molecular quenching step, then D star now will become D star. Q is the molecule that has been added. So D star plus Q, KQ will be equal to D plus Q star. Therefore, rate will be written as rate is equal to KQ D star Q. The concentration of fluorescence or fluorescer D star in presence of quencher Q, therefore now will be given as star is equal to IA divided by Kf as it is plus summation of Ki, K1 plus K quencher, concentration of quencher molecule in presence of quencher. This is the equation that is given. Now if D star and Q star are fluorescers concentration in absence and in presence of the quenchers, the respective quantum yields are, quantum yield will be written as Kf fluorescer concentration of D star divided by IA. This whole thing is rate of fluorescer FL. Fluorescence emission, we can write emission divided by rate of absorption of radiation, which is equal to Kf D star divided by IA, which is nothing but Kf divided by IA into IA divided by Kf plus summation of K1, which is equal to Kf divided by Kf plus summation of K1 at the ground state. Now quantum yield at excited state F will be equal to Kf D star divided by IA is equal to Kf divided by IA into 1 divided by Kf plus summation of K1 plus quencher concentration, rate of quencher concentration, which will be equal to, IA, which will be again equal to Kf divided by Kf plus summation of K1 plus rate of quencher concentration. When we divide these two equations, or the ratio of quantum yields of fluorescer D in the absence and presence of quencher Q will be given by Kf we have to write Kf divided by Kf plus summation of K1 divided by this equation will be equal to Kf, it becomes the reciprocal, Kf plus summation of K1 plus rate of concentration of quencher divided by Kf. Kf gets cancelled. What we are left out with is equal to Kf plus summation of K1 plus rate of quencher concentration divided by Kf plus summation of K1. When we simplify this equation, what we get is 1 plus Kq of Q divided by Kf plus E K1, which is equal to 1 plus this whole term is taken as proportionality constant, and therefore we get Kq tau concentration of quencher. Therefore finally we can write down ratio of this as 1 plus Ksv concentration of quencher. This equation is known as Stern-Volmer equation, and Ksv is the ratio of bimolecular quenching rate constant to the unimolecular decay constant. It implies that there is a competition between unimolecular decay process and bimolecular quenching process. Hence, the Stern-Volmer equation constant is having the characteristics of an equilibrium constant. The Stern-Volmer equation is linear in quencher concentration and the ratio of quantum yield values. Slope drawn for this ratio and Q will be equal to Stern-Volmer constant. Tau is the actual lifetime of fluorescer molecule in the absence of bimolecular quenching and is expressed as 1 divided by Kf plus summation of K1. Usually, the lifetime of fluorescer excited states are approximately in the order of 10 to the power minus 8 seconds, and the Stern-Volmer constant is of the order of 10 to the power 2 liter per moles. So as per Stern-Volmer equation, Kq tau is equal to Ksv. So the bimolecular quenching rate constant will become Kq is equal to Ksv divided by tau. If you put the values of Ksv and tau, that is 10 to the power 2 divided by 10 to the power minus 8, what answer we get is 10 to the power 10 liter per mole per second. That's it for today. Thanks for watching.